Okay, so what we're going to do is you should have gotten or received a sheet when you came in for lab today called Capacitors, a few interesting circuits. And this is both two things. It's a review sheet for a couple problems we've already practiced. And this is going to put a spin on some of the stuff we practiced already, because it's going to combine some past theorems that we learned about a couple weeks ago with RC circuits. So if you have this sheet, go ahead and take it out, and you'll need some scrap paper, you'll need a calculator, and what I want to do is I want to solve the first problem. And the way I want to do this session is I'll put the problem on the board, or you might have it here on the handout if you have the handout. Put it on a piece of paper, and then I'll give you a chance to solve it, and then I'll go through and show you the correct way to solve it, and we'll see if you thought about it the right way. So get a sheet of paper, pen, pencil, calculator, and if you have the handout, take that out. And I'm looking at the very first problem on the board, number 1 on the handout, and I will put it on the board, and then we'll talk about it. And at any point, if you have any questions, please ask. All right, so this is the first problem on the handout. The question says, how would you solve a circuit like this one? They want you to find the voltage across the capacitor at T equals 2 tau, and they want you to find the voltage across the capacitor at T greater than 5 tau. So 2 tau and T greater than 5 tau. Let's put that on the board. So we want to find VC at 2 tau and T greater than 5 tau. So that's what we want to solve for. So I'll give you a minute to think about how you might do that. And then if either you can't figure it out or just want to wait till I get through it, take a few minutes. And now this is exactly like the example I did in class. The difference is in class, we had a single resistor hooked up to the capacitor. So for that RC circuit that we looked at in class, it looked like this. And you were able to solve for the voltage across the capacitor or the voltage across the resistor in this circuit easily, either with the graph that I showed you in the last class, but more than likely the equations would be what you would use to solve that. So if you did the second capacitor, if you did the, not the second capacitor homework problem, if you did the example that we did in the last class, we actually found the voltage across the capacitor and the voltage across the resistor at, I believe, 30 milliseconds after the switch is closed. But in this circuit, you only have one resistor connected to the capacitor. Now you have, there's 1, 2, 3 resistors connected to the capacitor, That's one difference between the two circuits. And the second difference is those resistors are not in series. They're in series parallel. If they were all in series, we can just add them up into one resistor and have this circuit again that we know how to solve already. But when I look at this circuit, I got one capacitor connected to 3 resistors, and I have a series parallel circuit. So the question we're really trying to figure out, solve, is how would I solve for VC at these 2 times if I don't have a circuit like this, my normal RC circuit? If I'm given a more complicated circuit like this, how will I figure out the voltage across the capacitor and for these 2 times? So it's 1:15. I'm going to just pause for a few minutes to let you think about how you might do this, and if you can't figure it out, then we'll just do it together. So take 2 or 3 minutes. Don't worry about not having the correct answer, or maybe you do have the correct answer. I don't know. Just go ahead and try to think about how you might solve it. Okay, so I'll give you a couple minutes. I don't know if you're figured out anything yet, but just to kind of figure out how to approach the problem. Is it Nathan? Yeah. Do you have any suggestions, Nathan? Do you see what to do here? Or are you stuck, or what do you think? Any suggestions on how to approach it? And I'll give you a kind of a hint here. This is what we know how to do. This is like the example problem we did in class. So if you attended the last class, that's our basic RC circuit. You would know how to do that using the equations. The hint is this. Really, there's no way you can solve for these with all these resistors here. It's kind of complicated. So the question you want to ask yourself, is there a way to make this circuit look like this circuit? Because if there's some kind of way you can make this circuit, if you can simplify it so it looks like this circuit, we already know how to solve a circuit like this, a basic RC circuit. So can you think of anything that we've done in the past, or do you have any suggestions on a way I might be able to convert this more complicated circuit to a simpler circuit? Do you have any suggestions on how we might do that? Anything come to mind?
Mesh the resistors together.
Okay. So a lot of students do say that you would combine these resistors and they would go ahead and they would treat this as if it were a series parallel circuit, just like you said, and they put the resistors together and get one resistor. So you're kind of correct. You're correct, but you got to do it a certain way. So in putting the resistors together like you suggested, the way you want to do it is you don't want to know what the total resistance is looking this way in the circuit. You want to know what total resistance the capacitor sees. So it might help if I do this. If I put these little terminals on there, hopefully that made you think of when we had to do Thevenin's theorem. If you remember, when you Thevenize a circuit, let's say instead of a capacitor, let's say I had resistors like this. I had a resistor here, and here, and here, and a battery. So instead of a capacitor here, let's say I have a resistor here. I tell you that this is R1, R2, R3. If I ask for the total resistance in the circuit, which is what we're looking for, remember there's two of them. There's a resistance looking this way, which is the resistance that the voltage source sees, and then there's the resistance looking this way, which whatever resistor you name as the load, that's the resistance the load sees. And the way you do that is by Thevenizing the circuit. You got a Thevenin circuit, has two components. There's a resistance RTH and a voltage source VTH. So to Thevenize this circuit, you would remove the load and you would mark the terminals, A and B. And then to get the voltage, you would put your voltmeter here. And what we said was, if there's a resistor hanging there with no current going through it, and there's no voltage drop across the resistor, so whatever voltage you have here, you would have here. So the voltage between A and B is the same as the voltage drop across R2, because there's no current going through R3 to drop the voltage. So connecting here is exactly like connecting there. We mentioned this in class a couple times. So understanding that, you would just find the voltage drop across R2, and that would be VTH. And then to find RTH, you would short this out, and you would look into this terminal, and what you see is this resistor in series with the parallel combination of these two, and that will give you the value of RTH. That would be the value that the load resistor sees. If I were to put it back in the circuit, that load resistor, it will see a value of RTH. Well, how does that apply to this? Well, it applies to this because of what I said earlier. I'm not interested in how much resistance the battery sees. I want to know how much resistance the capacitor thinks is in the circuit. How much resistance does the capacitor see? Because that is the resistance I will put into my Thevenin circuit. And if I Thevenize this circuit, I'll end up with a voltage source, a resistor, and then I'll put the capacitor there, which is acting as a load. And now this looks like my RC circuit that we've been doing, that we did in the last class. So the key is to Thevenize it. Remove the capacitor, mark the terminals, find VTH and RTH. So I don't know if you remember the steps to that. I kind of just went over it, but that's my hint. It's not a hint anymore. That's what you got to do. You got to Thevenize the circuit and then use the Thevenin circuit to find these values right here. So again, I want to pause a few minutes. I don't know how well your Thevenin skills are, if you're kind of rusty on them, but go ahead and try to Thevenize this circuit. We're going to assume that the capacitor is going to act as the load, which means that's what you're going to remove, and then get your values for RTH and VTH. Now wait about another 3 minutes. You keep working, and then I'll come back, and if you
You're muted.
Thank you. I forgot I muted it. So I want to go through and walk through the steps of Thevenizing the circuit. And so we're going to make that circuit look like a Thevenin circuit, which happens to look like the RC circuit that we've been working on. So I need values for VTH and RTH. All right, so when you Thevenize, you remove the load, mark the terminals, call one terminal A and B. Then we have A and B in Thevenin circuit. Now, we find the Thevenin voltage first, and as I said before, if I connect my voltmeter between A and B, then I'm across resistor R2. Just to emphasize this, R3 doesn't matter because since R3 is just hanging there with no current going through it, no current can flow through it because there's an open circuit between points A and B. So since no current can go through R3, there's no current going through a resistor, it cannot drop the voltage. So the voltage across R2 cannot be dropped across R3 since there's no current through R3. And what that means is whatever the voltage drop is across R2, that is going to be my voltage between A and B, which is going to be my Thevenin voltage. So to solve the problem, I just got to figure out the voltage drop across R2. And there's two ways to do that. I can use the voltage divider rule. I can use Ohm's law. I like to use the voltage divider rule only because it's faster. The voltage divider rule says if I want to know the voltage across resistor, put that in the numerator. So I'm going to put the 6 mega ohm in the numerator. Divide by the total resistance looking this way. It's looking that way. What is my total resistance? Well, total resistance looking this way would be only the resistors. Well, this resistor again would not be involved because it doesn't have any current going through it. The battery looking this way only still sees the opposition of R1 and R2. It only sees the opposition of resistors through which current would flow. And since current would just go around this loop, from the point of view of the battery, these are the only two resistors in the circuit. So it's series. I take this one plus this one, I get 9 mega ohms. As you can see here, the units cancel out, which is nice. Just got a number there with no units. So Kirchhoff's voltage law says take the resistor, you want to know the voltage across, put that in the numerator, divide by the total resistance in the circuit, and then you multiply that fraction by the total voltage. And that'll give you VTH. In this case, I get 6 volts. So what that tells me is, even though there's a 9-volt battery over here, the capacitor sees only 6 volts. It thinks there's a 6-volt battery there. And so I can put that over here, that VTH is 6 volts. For the second part of the problem, I got to find RTH. And the way we do that is we first set the power source to 0. The power source is a voltage source. We replace it with the short circuit. If it's a current source, we replace it with an open circuit. It's a voltage source, I replace it with the short. Now, notice that R1 and R2 are tied together right here at that point. And once I put the short circuit here, once I short that battery out, that ties the other side of R1 and R2 together. So R1 and R2 are actually in parallel. So if I'm looking in this way, looking back in this way, to see what resistance the capacitor sees, what that capacitor is going to see is it's going to see R3 plus these two in parallel. R3 plus the parallel combination of R1 parallel R2. So that value right there will give me RTH. If I put my numbers in there, I've got 3 mega ohm plus, no, I got 4 mega ohm. That's 4 mega ohm. Yeah, R3 is 4 mega ohm. Got 4 mega ohm plus 3 in parallel with 6. So you gotta give me the equivalent resistance for those two in parallel. You can use the product over the sum, or you can use 1 over R rule, but since I got 2 easy resistors, for the parallel circuit, I'm going to use this one, the product over the sum. So if I use that one, I'll have, for R1, I'll have 3 times 6 over 3 plus 6. So on the top, I have 18, and on the bottom, I have 9. That'll give me 2. But that actually is in megohms, so it'll be 2 megohms. So my resistance from the point of view of the capacitor is going to be this 4 megohms in series with this 2 megohm. That's going to give me 6 megaohms. So that's what I get for RTH. It's going to be 6 megaohms. Let me pause for a minute because here's where things get interesting. Notice that the voltage source sees one thing. The voltage source sees, number one, it sees a series circuit. It thinks the only resistors that's in the circuit is R1 and R2, and those resistors are in series. We got a total resistance of 9. Well, the capacitor sees something totally different. Number one, it doesn't see a voltage of 9 volts. It only sees a voltage of 6 volts. Number two, whereas I have a series circuit over here that the voltage source sees, notice the capacitor sees a more complex circuit. It sees R3 in series with the parallel combination of R1 and R2, which is expressed right here. So what it sees is 6 megaohms. So now I can take this capacitor off and put it over here on this side, and I can do my analysis. Let me see what value cap. It's a 10 microfarad cap. So now, having Thevenized this, we are able to apply the same method that we looked at in the last class. We can use those equations. Now, we can go ahead and answer this one right away because it says find VC at t greater than 5 tau. You know at t greater than 5 tau that you're in steady state. At that point, the capacitor is fully charged. Now, even if you, over here, a lot of students will say, all right, we're at steady state, the capacitor is going to be fully charged, so it's going to reach 9 volts. Only when you Thevenize can you see that the actual voltage, the max voltage the capacitor C, the actual voltage is not 9, it's actually 6. This capacitor thinks it's hooked to a 6-volt source. So for this answer, at t greater than 5 time constants, it's going to be 6 volts across the capacitor because it takes 5 time constants for the capacitor to fully charge. It's going to charge it all the way up to whatever the Thevenin voltage is. That's the first part. So that's easy. I'm going to pause a minute and let you think about how you would do the second part. Do the second part. Now, this one is like the one we did in class. So if you have that handout, convenient, take a look at the handout, take a look at the notes from the RC problem we did in the last class, and this is done exactly the same way. So again, I'll be quiet. I'll give you a few minutes to work on it, and then we will attack it together. Okay, did you come up with a solution or not? Okay, you didn't answer, so I'm going to assume you did not. So it's easy to find the voltage at 5 time constants once you realize that this capacitor doesn't charge up to 9 volts. It only charges up to the Thevenin voltage. So it's going to charge up to 6 volts. So at 5 time constants, if I have a basic RC circuit, which this Thevenin circuit now looks like, the voltage across the capacitor at steady state is going to be whatever the source voltage is. So in this case, it's going to be 6 volts. Now I got to figure out, okay, what is the voltage at 2 tau? And for that one, since this is a charging circuit, I got to figure out which equation to use. I gave you a list of 6 equations, 3 and 3, 3 for charged circuits and 3 for discharged circuits. Clearly, this is a charging circuit. When you hook it up, capacitor is going to charge up. So I'm going to use this equation for VC. VC equals total voltage times 1 minus e to the minus t on tau. That'll be the equation I use for VC. And if I put my numbers in, this is equal to 6 times the quantity, 1 minus. Now this exponent right here, that exponent is minus t over tau. Well, if you remember that tau is just RC. Tau is just RC. So since they have that tau there, I can just put that down there because this is going to be RC. I can put the actual time in seconds, or I can leave it in terms of tau. I know R times C is tau, so that's tau. And the time you want to look at it, again, I can have that time in seconds, like we did in a practice problem we did the other day. But here they have it in terms of tau. They say look at it at 2 tau. If you know what tau was, you can convert it to seconds. So if I told you tau was 5 seconds, then 2 tau would be 10 seconds. But often it's more convenient to leave it in terms of tau. And so if I got tau in the denominator and the t I'm looking at, the time I'm looking at is when it's at 2 tau. I got to put the negative sign in there. Then you can see what's going to happen. The taus cancel out, and I'm left with a minus 2. So instead of entering all this in your calculator and using all those double parentheses to do the division here, it's best to just come off to the side, do the division, get one number, and then put that number right here. So we did all of that to say that t equals minus 2. So that's our answer right there. So we'll have 1 e to the minus 2. And that's what I want to calculate. So go ahead and see if you can calculate that. I need to find my calculator. And I'll do the calculations right along with you. All right. So I'm going to put this into my calculator. I got 6 paren 1 minus second function e minus 2 close. I get 5.19 volts. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . 5.19 volts at 2 tau. So here's the takeaway. Here's the thing to remember. If I give you a basic RC circuit like this one, it's pretty easy to do. You can use this equation and the other 5 equations that I gave you in the last class to solve it. If I give you a circuit that has more than one resistor in it, it doesn't look like this, and I ask you to find the voltage at certain times, then what you want to do is stabilize the circuit and treat the capacitor as if it's the load. You pull it off, you get the Thevenin equivalent circuit, and that Thevenin equivalent circuit is what you will hook the capacitor back up to. And whatever the Thevenin voltage is the voltage that the capacitor actually thinks is in the circuit. And whatever your RTH is, that's the resistance that the capacitor actually thinks is in the circuit. So by Thevenizing, it's just a really, really powerful technique that allows us to solve circuits in a pretty simple way. So, do you have any questions on this problem? Any questions? Okay, well, if there are no questions, I want to move on to the next problem. Now, this one we've done a couple times. We've done at least one time. They give you a circuit, number 2, and they want you to find the voltage across each resistor at t equals 0 and t greater than 5 tau. So while you're working on that, I'm going to put the circuit on the board. All right. I want you to, I'll put the circuit up here twice and we're going to do it for each time. They want you to figure out the voltage across each resistor at t equals 0. This is the circuit I'm going to solve for t equals 0. And I want to repeat that on this side, and this will be the other time they want us to look at. All right, so for this one, same circuit. This is for T greater than 5 tau. Okay, so a couple more minutes, and then we'll work it together. All right, so for this first one, they want us to figure out the voltage across each resistor at T equals 0. And at T equals 0, that's one of the special times for capacitors. At T equals 0, the capacitor behaves like a short circuit. So what I got to do is go in here and replace each capacitor with the short, and then make sure I understand what's happened to the circuit when I place the short in the circuit. So for example, if I replace C1 with the short, all it's going to do is connect R2 directly to that bottom wire through the short. And if I replace C2 with the short, all it's going to do is take the top of R4 and connect to this node right here. And hopefully you recognize that as just a parallel circuit. I have R1 is 3, I have R2 and R3 in parallel, 12 in parallel with 4. So I want to find the voltage across each of these. So what I want to do is to turn this into a series circuit, and then my problem will be really, really easy. So for this resistor, that's R1, that's 3K ohm. It's connected to 10 volts. And then I got to do, these two are in parallel, so I got to do 12 parallel 4. Get my calculator and see what that is. 12, 4, gives me 3. So this equals 3 K ohms. So then over here, I have 3 K ohms. Now, this point right here, this point, and this point is right here and right here in the circuit. So if I find the voltage across these two, then I found the voltage across R2 and R3, and that's exactly what I want to know. Well, I can easily see from the circuit that since both of these are the same value, that each one's going to get the same voltage, so it has to be 5 volts. So I got 5 volts across this one, 5 volts across that one. So I'll go ahead, that's what they wanted, was voltages. So I'll just put, I'm going to erase these. So this has 5 volts. This has 5 volts. And this has 5 volts. So that's what I want to know. What is the value of the voltage across each resistor at T equals 0? At T equals 0, the resistors are short circuits, and this would be what I would see at T0. 5 volts across each resistor. Now the second part, they want you to do a problem where you do the same calculation, but this time instead of T being equal to 0, the other special time that we talked about was T greater than or equal to 5 tau. So remember what a capacitor looks like at 5 tau. You place that capacitor with its value and then see if you can do the analysis, see what it looks like at t greater than 5 tau. So I'm going to wait 2 minutes, let you think about it, and then we'll do it together. That's fine, Nathan. Go ahead and thank you for attending. I will keep going with the recording, and I will put this on YouTube so you can watch the link. Thank you so much. Okay, so we're going to go ahead and complete this other problem. At 5 time constants or greater, each capacitor acts like an open circuit. So this capacitor is going to open. And what that will do is prevent any current from getting to R3. So in this circuit, since no current can get to R3, V3 is going to be 0 volts. This capacitor, when I open it up, is going to stop any current flow through R2 and R1 because I have all open circuits. There's no way for current to go from the positive terminal to the negative. Therefore, it goes across each resistor is 0 volts. So we did this problem. We did one of these problems before in class. You practice it. I think this shouldn't be too big of a thing. So on the final exam, expect something like this where you have to solve a circuit with capacitors in it at T0 and T greater than or equal to 5 tau. Okay, so that takes care of problem number 1. And problem number 2, the Thevenin problem, and then the practice problem with the shorts and open circuits, equivalent circuits with capacitors. Now, number 3 is entitled a burst of energy. A burst of energy, and I'll explain why that is. So take a second and read the document, problem number 3, and while you're reading, I'm going to go ahead and put the problem on the board, and then we'll talk about the problem. And now give you a chance to solve the problem, and we'll talk about why things are the way they are in regards to the problem. So go ahead and get the paper out, start to do your analysis, figure it out. I'll give you some time to do that, and then we'll proceed. All right. So, given this problem, they want us to find a couple things. They want to know what is the maximum current in the circuit when S1 is moved to position 1. How long in seconds will it take C1 to fully charge? And what is the maximum current associated with S1 when S1 is moved from position 1 to position 3. How long will it take in seconds for capacitor C2 or C1 to fully charge? Well, we can answer all those questions, but let's first look at the circuit. And this is one of those circuits where I use a 3-position switch. I could have used a 2-position switch, position 1 and 3. Either the circuit is, if it's at 1, it's charging up. If it's at 3, it's discharging. I like to use a 3-position switch here because with a 3-position switch, I can have position 1, a charge circuit. Position 2, it'll hold the charge, or hold the voltage. Position 3, it will discharge. So I'm gonna, and notice I also have a light bulb. And the light bulb is interesting because they give us the ohmic value of the light bulb filament. So this is like a really low value resistor. That's the resistance of the light bulb. I'll call it arc bulb, RB. So here's what's gonna happen. When I go from position 1 to position 2, the capacitor is going to charge through the 1,000 ohm resistor. And now when it's fully charged, I can move it to position 2. When I go from position 2 to position 3, now I have a discharge circuit and the light bulb will light up. 2 different taus though, because the tau for this is R times C, so 1K times 10 microfarads. And the tau for this is 0.1 times 10 microfarad. So this charge, the charge tau is a lot less than the discharge tau is a lot smaller than the charge tau because the resistance here is 0.1 and over here it's 1,000. So it's a big difference between the two, like difference of like 10,000. So the very first thing you want to do here, and again, I want to pause and give you a few seconds to do it. I want to know what is the maximum current when S1 is moved into position 1. So this is one of those principles we talked about in the class. So see what you can do with it. I want to know when I move, assuming no initial charges in the capacitor, when I move the switch from position 1 to position 2, what will be the max current in the circuit? I want to pause and let you think about how to do that, and then we'll work it together. Okay, hopefully that's enough time to work probably both problems out. What is the maximum current when S1 is moved from position, there's a typo there, it says form, but it says from position 1 to position 3. Assume the capacitor is fully charged. So we charge the capacitor up to 9 volts. When we move from position 1 to 3, we got 9 volts across this low resistance. So watch what's going to happen. When we move from position 2 to 1, the max current was 9 milliamps. That's the most current we can get to flow in the circuit. But now, let's look at what we got. That capacitor is going to charge up to 9 volts, or it's charged up to 9 volts. But it's going to discharge through 0.1 ohm. You divide 9 by 0.1, you get 90, not milliamps, you get 90 amps. So where this current was 0.009 amps, the discharge current is 90 amps. That's a huge number, a huge amount of current. And you might say to yourself, well, gosh, how do we get such of a large current out of a small device? Well, the difference is in how long it takes the energy to flow in and out of the capacitor. When you're charging the capacitor, that tau, if you remember, tau is 10 milliseconds. Here you're going to find the tau is a lot shorter. And so that means it's a lot of energy, but it's a lot of energy fast. This is a lot of energy over a longer period, less energy over a longer period of time. How long will it take in seconds for C1 to fully charge? Well, remember before, when I was in position 1, it took 10 milliseconds for tau, 50 milliseconds to fully charge. They want to know how long will it take the capacitor to fully discharge. So I got to find tau again, but this time we'll call it TD for tau discharge. And again, it's going to be R, but this time the R I'm going to use is that one. The resistance of the bulb times the value of the capacitor. So I got 0.1 times C, which is 10. Actually, no, it's 10 times 10 to the minus 6 farads. So if I do my math, let's just do this part. If I multiply 0.1 times 10, that's going to give me 1. I got 1 times 10 to the minus 6. That will be in seconds. So that's 1 microsecond. It took 10 milliseconds for tau here. Here we got a tau of 1 microsecond. To fully charge, it took 5 times this number, or 50 milliseconds. For this fully discharge, it's going to take 5 times that number, or 5 microseconds. So another way to look at that is, if you divide these two numbers, if I divide 50 milliseconds by 5 microseconds, and what I'm going to get is, do the math here. So I have 50 divided by 5. Put it in wrong. 50 milli divided by 5. I get 10,000. This ratio is 10,000. What does that mean? it means that the capacitor discharges 10,000 times faster than it charges. So when I mentioned earlier, you get a lot of current over here, but you get that current at a quicker time. Here you get, 10 milliseconds is quick, but 5 microseconds is way quicker, 10,000 times quicker. Okay? So I would say if you can work these problems, at least you understand the concepts, you should be okay on the final exam, which you'll work on over the weekend and you'll hand it in next Tuesday. Now, this is not all that's on the test. There's some other things that I listed for the final, but these are the main ones where students get stuck kind of on the capacitor stuff. So you want to make sure you understand what's on here. No, nobody's hearing. I'm just recording this. But if anybody has any questions, you can text me. You can email me. Texting me is the best way. And this will be available up on YouTube as soon as Blackboard finishes rendering the recording. So you guys have a great rest of the day. I will see you in class tomorrow, and stay safe.